Okay, today I thought we'd start introducing the concept of drag or air resistance into our projectile motion. Pretty common effect we need to understand in day-to-day life. And what we'll do is we'll look at, if I throw an object straight up in the air, so just one-dimensional vertical motion for now, at some speed v, but it's subject to a drag force that's a linear drag force. In other words, the drag force is proportional to the first power of the velocity. I want to know, well, how high does it go? And also, when it comes back down, what is its speed upon landing? We'll see that to do this, we're going to need to solve a transcendental equation. I'll talk about the Lambert W-function a little bit, although we can do some approximations if we don't want to do that. So first off, here's our drag force. Notice that I have a negative sign multiplying the vector v, so it always points opposite the direction of the velocity instantaneously. The coefficient is sometimes just written as b or some generic constant. I'm actually going to write it as m, its mass, times some other constant because it's a little cleaner to factor out a mass. And then this gamma constant will be what I call the linear drag coefficient. We'll find a couple other terms that show up naturally in the context of linear drag, and I'll give them some definitions when we get to them. So the first thing we should do is recognize that an object that's subject to linear drag is also subject to gravity if it's a projectile motion problem, so we should write down Newton's second law. So the net force in the y direction, which is what I'll call my positive vertical direction as being up, will depend on which way the particle is moving. Let's start by looking at the upwards part of the path. So as it's going upwards, there are two downwards forces. Gravity is always down, and the drag force will point down because that's opposite of the velocity. On its way back down, the drag force would actually point up, but we'll get to that later. So I'll have a minus mg, that's the usual gravitational force, and now I will have a minus m gamma vy. That's the drag force. Those are my two forces that are acting. And of course, we know by Newton's second law that this is the mass of the object times what I'll write as vy dot, the time derivative of the velocity, the acceleration. Now, although I could go integrate this as a function of time, I'm a little more interested in its velocity as a function of position because I've got this max height I might be interested in. So let's go ahead and use our usual chain rule trick to rewrite vy dot, which is dvy dt, as dvy dy dt, but of course dy dt is y dot. So this is y dot, which is vy. So this will be dvy dy times vy. Now I've got a derivative with respect to position instead of time. Notice that the m's cancel out. That's partly why I decided to factor an m out here. And we'll be left with vy dvy dy. I'm moving that to the other side. Will be minus g minus gamma vy. Now this is a nice separable equation, so let's separate variables. I'm just going to pull everything except for the minus sign down to the denominator here. And I will move the minus sign and the dy to the right-hand side. The next thing we want to do is integrate both sides. We do want to be a little particular about our bounds of integration. So notice I'm looking at the upwards path. I start at height 0, and I'll end at height capital H. If you want to do this for a generic y, that's fine, but it'll be a little easier if we just look at ending at the max height. My initial velocity in the y direction is v naught. That's my launch speed. And if I'm going to the max height, I know that this ends at 0. The y component should be 0 once I'm at the maximum. Notice that because I have 0 on top and v naught on the bottom, I probably want to swap that, which would pick up a minus sign. But that minus sign will exactly cancel with this minus sign, so I'll just do that right now. That will leave something kind of nice on the right-hand side, which is literally just the number h. Kind of nice. On the left-hand side, I need to do this antiderivative. There's a lot of ways of doing it. I think I'm going to do a tricky trick. So I've got 0 to v naught. I am going to, first of all, multiply and divide the whole thing by gamma. That'll put a gamma up here, which will kind of match the one that'll be in the denominator. And then I'm going to add and subtract g in the numerator. This is all dvy. And the reason for this is that this whole first term is just a 1, which is easy to integrate. Then I just have minus a constant, which is g, over g plus gamma vy. And that's going to end up just being kind of an easy natural log. So let's move things over to the other side a little bit here of the board. So this integral will become a 1 over gamma. The antiderivative of 1, unsurprisingly, will leave behind a v naught. Don't forget the 0 is being plugged in, but that's not going to change anything. And then this antiderivative can be done with a real quick u substitution. Maybe I'll write that in. I'll just let u equal g plus gamma vy. So I can pull out the g that's on top. That's a constant. I'll go ahead and write this in one additional step. The integral is now going to go from v equals 0, but that's actually u equals g, up to v equals v naught, but that's actually u equals g plus gamma v naught. And notice also we have to change our Jacobian, or we have to introduce a Jacobian. du is going to be gamma times dvy. So my dvy term will have another 1 over gamma in it. So I'll have, let's write it as du over gamma all over u, and this equals h. Now it's quite easy. I have v naught over gamma minus g over gamma. Integral of 1 over u is just natural log. And I can just go ahead and plug in the top and bottom. Remember, they're being subtracted, but a difference of logs is the log of the quotient. So I'll write that as gamma v naught plus g all over g. And on the right-hand side, I have h. So there's a nice relationship that lets me find h in terms of my initial speed, g, and gamma. Now, we do see quite a few instances of the same factor kind of showing up over and over. Let's define a couple things that'll be useful for a lot of drag problems. Let's define a time, tau, which is 1 over gamma. Notice way back here that since I need something like mass times acceleration, I need gamma to have units of 1 over time. So it makes sense to say 1 over gamma is some sort of characteristic time. I'll just call it tau. Let's also define what I'll call Vt as g over gamma. Oh, and this, by the way, should have been a gamma squared. There's one gamma here and there's one gamma here, so that's a gamma squared. The reason I'm calling this Vt is because this is actually the terminal velocity. I haven't shown that, but we can quickly go back up here and check that if you wait long enough so that Vy is a constant, or at least approaches a constant, Vy dot will go to 0. And if I solve for Vy here in that instance, it'll be negative because it'll be downwards, but its magnitude will just end up being g over gamma. So we call this the terminal velocity, or really this is the terminal speed. Velocity points downwards. And I'll call that Vt. It's built out of constants appropriate to the problem, but it's easier to see what the units are at a glance. Oh, it's v, it's a speed. So rewriting this in terms of those quantities, I can see that my first term is just going to be v naught tau, which makes sense, that is a distance. And then I'll have minus, notice I'll get a vt times tau, times this natural log of, well, let's factor the g into these two terms, 1 plus, and then the gamma over g is 1 over vt. So there's our first result. The height that you'll reach, launched at some speed v naught, in the presence of a damping or drag factor gamma, will be this. All right, let's save this over here. And then we're going to find out how we can relate this to the downwards trip. Okay, so those are now over to the side for future reference. We don't actually have to redo anything to find out how speed and height are related on the downward strip, because as this falls downwards, we can just sort of imagine running this whole thing in reverse. It's just that our initial velocity is now replaced by our final velocity, which is negative our final speed, because of course it's moving downwards when it hits the ground. Now that v final I don't know, but that's kind of the purpose of this problem. Let's go ahead and just write things in terms of that. How would we do that? Well, this first bit, v naught, is going to be replaced by a negative v final. Again, we're imagining running this up and down motion sort of in reverse. I would start with a negative vf and then get to height h by just substituting into the same formula. The second term starts the same, vt tau, those are just constants, those don't change. But now inside of here I'll have a 1 minus v final over vt. So that's kind of nice. We didn't actually have to do any extra differential equation solving. You could if you want to double check this, but there is the height written in two different ways. If you're worried that this is like a double negative or something, so my height is negative, no, it's not. This natural log will also be negative and you'll get the same positive result for that height. Next, I want to, well, set these equal, which I did, and solve best I can for v final. So first, let's write that up here. I'm going to do another little simplification just to make life a little easier. I am going to introduce the variable u to stand for v over vt. It's basically a reduced speed. It's a speed in terms of the terminal velocity. So I would call u naught v naught over vt, and I'll call u final v final over vt. Just because those ratios show up everywhere, and I can write this in a nice dimensionless form. So setting these equal, I will go ahead and move this to the other side, and I will end up with, I guess I'll write one term first. So v naught plus vf, and yes, I've not divided yet, so it is still in terms of v. That'll be the left-hand side. And then on the right-hand side, I'll go ahead and move this term over. So I'll have equals positive vt tau, positive natural log 1 plus v naught over vt, and then there's still this minus sign that's over here, so minus the natural log of 1 minus vf over vt. And now I'll do this trick. Notice the taus cancel from both sides. I'll divide the vt over, which will give me u naught plus u final on the left. On the right, when I do this subtraction of logs, I'll end up with the log of a quotient. 1 plus u naught, 1 minus uf. Now, as it stands, we can't go any further. Uf shows up inside of a log and also as a polynomial outside. So this is a transcendental equation that cannot be solved in terms of our usual familiar functions. So we could just sort of leave it at this and say, well, okay, at least I have it implicitly defined. But in the spirit of, I don't know, seeing something a little different, let's actually solve this using a very special function that is custom designed for this exact purpose, which is the Lambert function. Let me go ahead and write its properties on the board. Okay, so here it is. The Lambert W-function is the function that is the solution to this transcendental equation. If I have something like y times e to the y equals x, and I want to solve that for y, then y is the Lambert function, the W function of x. So it's the inverse of this. Now, it should be noted that actually this function does not exist on, or I should say, is not single valued on all of the possible domain of solution to this equation. So if x is less than 0, there's actually two solutions. We call them the two branches of the Lambert function, w0 and w minus 1. If x is positive, then there is a unique solution here and there's no issue. For us, pretty much everything will be positive, so it won't be a big deal. And actually, even if we did have to go into negative land, we're only going to use the so-called W0 function. So I'm not going to bother writing that down. That's always the branch we'll be using pretty much for all physical applications. So what I want to do is rewrite this in some way that looks like this so I can immediately apply the definition. All right, we're trying to find UF. So the first thing we should do is, I don't want to log here, I want to ease. So let's exponentiate both sides. Okay, I'll go ahead and multiply this over, and then I am trying to separate out the U-naughts, which are basically my x here, and the UFs, which are the thing I'm trying to solve for. So let's multiply over. We'll have, and I'll go ahead and expand. So I'll have e to the U-naught, e to the UF times 1. Notice I did actually split them up because I can do that with exponent rules. Minus UF e to the U-naught, e to the UF equals 1 plus U-naught. Okay. I do see a common e to the U-naught on both of these terms, so I'll go ahead and divide that over, and then I'll factor out this e to the UF. So I have 1 minus UF e to the UF, guess I could have left it in that form, equals 1 plus U-naught e to the negative U-naught. Okay, the next thing I'm going to do is I'm going to swap this negative over and make it UF minus 1. At the same time, I'll put a little negative on this side. Why am I doing that? Because I have a negative sign here I really can't get rid of, so I'm trying to make these negatives match. The y here should match up. I'll have e to the minus U-naught. I left a gap there because now I want to try to make these two exponents look similar. So I have an e to the UF. Boy, if only I had a minus 1 up there, then this side is ready to go. It's got the same form in the exponent and the prefactor. This one is almost there too if I could just get a 1 up there. Well, guess what? I can do both of those by just doing a minus 1 here and a 1 plus on this side. It's still a minus 1. Basically, I divided both sides by e. So on this side, I'll end up with UF minus 1 in the exponent. On this side, that e to the minus 1 is what I just added in, and then it's multiplied by e to the minus U-naught, so I can factor out the minus sign, and now we're done. I can take the inverse, if you want, inverse Lambert function of both sides. This side will be UF, the thing I'm looking for, actually UF minus 1. And the right-hand side will be the Lambert function of all of this junk. Now all we have to do is just add 1 over, and I've solved for UF, which is my final speed divided by the terminal speed. This bit inside of the argument is actually negative. There is a negative sign out here, so we maybe are worried a little bit about the branches. We do still want to use the principal branch here. Maybe at some future video I can go into what the other branch looks like. It goes to negative infinity in a weird way, so it's not applicable in physics. But these are all knowns, and we do have an explicit formula for UF, or for V final, as VT1 plus this Lambert function. Though it's not like any of your graphing calculators have the Lambert function plugged in, so probably would have to use a computer to actually calculate this. At any rate, that does solve our problem. We now have the speed at which my projectile hits the ground in terms of the initial speed through this U-naught. Now, it should also be noted that that final speed will definitely be less than the initial speed. There's a lot of ways of seeing that. One would be to look at this and really try to parse out the ordering or valuation. I wouldn't recommend it that way. Instead, just think of conservation of energy. Drag, by its very nature, is always providing negative work on this system because the force is always opposite the displacement at every instant. So, of course, that's going to rob kinetic energy from the system. So even landing at the same height, I'll end up with a lower speed. We can also, if desired, take a look at some of the low drag limits. So if we want to take gamma to 0, that's the same thing as taking tau to infinity and vt to infinity, this height expression, if you expand out your natural log to the first couple orders, the first term will give you something that cancels off this first bit, so that's not very interesting. The second order term, the quadratic term, will have a v naught squared in it, and then I'll have a tau over v tau that comes up, well, with one of the v taus canceling, and that will give me a g. So you will recover the v naught squared over 2g that we expect in the dragless limit. The limit just has to be taken appropriately. We'll probably be coming back to our linear drag and looking at it in 2 dimensions and maybe asking a few more questions, but I think this is a good first blush at this type of equations of motion and analyzing it using the separation of variables, and maybe a little taste of the Lambert W function, which is maybe less familiar. QED.